I'm going to finish up some topics or finish up the rest of chapter 3 actually, just by making some comments on, brief comments on the last two sections in the chapter. Section 3.9 is on the classical solution of difference equations. I don't think anyone in this course has actually studied difference equations in a previous course, unlike it is expected that you've taken the differential equations class. But just as we had for continuous time systems and the classical method, the solution consists of the natural response and the natural response is is the portion of the response that consists of all the sum of all the mode terms, and then the forced response. Okay. These are slightly different than our zero input and zero state responses. Our zero state response will typically include some mode terms. It's the mode terms necessary so that all the initial conditions are actually zero. So the total solution is the same whether you work it out classically or via convolution. The method that's introduced here to get the zero state response, you'll get the same total response. Just the terminology and the two components of the solution are different using the method we've been using, and then the classical solution method. And then just briefly a comment on stability for discrete time systems. For bounded input, bounded output stability, the condition in terms of the impulse response is that the impulse response has to be absolutely summable, or that if we evaluate this sum, the result has to be finite. That's the condition for bounded input, bounded output stability. Asymptotic stability depends on the actual position of the roots of the characteristic equation. And the magnitude of the roots has to be less than 1, or said another way, all of the roots of the characteristic equation have to lie within the unit circle on the complex plane. So again, generally we can represent our characteristic roots as complex numbers, so they'll be positioned somewhere on the plane, on the complex plane. Okay. They might be in the right half plane. Some of them might be in the left half plane. Right half and left half planes are unimportant as far as stability is concerned for discrete time systems. But if I draw the unit circle here, and that's the circle with a radius of 1, so it'd be 1j on this imaginary axis. A point on the unit circle would be j. Another point on the unit circle would be minus j. Plus 1 and minus 1 are also points. On the unit circle. This is the real axis. Our condition for asymptotic stability is that all of our roots, they may be real, they may be complex, but all of the roots have to lie within the unit circle. Mathematically, if we express our roots in polar or exponential form, the magnitude of the roots then has to be less than 1. Otherwise, the system is either marginally stable or unstable. And if we have any root outside the unit circle, the system is unstable. The complete set of rules regarding marginal or stability and instability are actually given in your textbook. I want to work through, though, now a complete example finding the total response 3.8-10, where we're given the following difference equation: y of n plus 1 plus 2 y of n is equal to x of n plus 1. And this is what we would say the difference equation is in the advanced form. Okay. And then we're given the initial condition that y of minus 1 is equal to 10, and we want to find the response to this input, e to the minus n u of n. Okay. We'll start with the zero input response. Again, our characteristic polynomial, we can write the difference equation in the operator form, and then replace the operator with gamma. I'll go directly to the characteristic polynomial. It would be gamma to the first power plus 2. Again, these coefficients come down as multipliers, and then the advance becomes a power here, so this would be gamma to the first power plus 2. And we're dealing just with a first order difference equation. I set this equal to 0 to obtain the characteristic equation, and then solve. I get this system has a single characteristic root of minus 2. This, of course, we've just talked about stability. Since the magnitude here is greater than 1, the magnitude of this characteristic root is 2. This would correspond to the difference equation of an unstable system. The system is unstable. So our zero input response then is just, we've got an arbitrary coefficient, and then I'll have gamma 1 to the n power, or minus 2 to the n power. So this is the form of our zero input response. I can apply the initial condition. This is equal to 10, so that's c. Minus 2 to the minus 1 power would actually be minus 1/2. And then, so from this I get that c has to be equal to minus 20. So I get for our zero input response, y0 of n is minus 20 times minus 2 to the n. Okay. Now let's look at the zero state response. For the zero state response, we need the impulse response of the system. That will be given to you. Later in the course we'll see how to determine the impulse response actually from the system transfer function. But the impulse response of this particular system is minus 2 to the n u of n. So I get the zero state response by convolving the input with the impulse response. just going to take the easy way out here and look this up in the table. Recall that our x of n and for this problem is e to the minus n u of n. So this is in the form in gamma 1 to the n and then gamma 2 to the n. So looking this up in the table, we get as the result of this convolution 1 over e to the minus 1 plus 2 times e to the minus n plus 1 minus 2 to the n plus 1 all times u of n. Again, you should verify this, work through and get this, make sure you get the same result when you evaluate this convolution using the table. I can I'll simplify this a little bit by multiplying the ratio out in front, numerator and denominator, by e. So I'll get e over 1 plus 2e, and the rest of it stays. I'll leave the same. And then finally, the total response is the sum of the zero input response from the previous board. That was minus 20 minus 2 to the n, and then plus e over 1 plus 2 to the e to the minus n plus 1 minus 2 to the n plus 1 u of n as our total solution, closed form solution to this particular problem. So this concludes our study of the analysis of discrete time systems in the time domain. In subsequent chapters, we'll look at how to do analysis of these systems in the Z domain or frequency domain.